The law of sines in mathematics is used a lot within triangles, and the benefit of using the law of sines is when we have a triangle that's not necessarily a right triangle. This applies for all types of triangles. And it's stated as a sine of a degrees over little a, and little a represents the segment that's across or opposite of the angle that we're taking the sine of. And that goes out through the whole triangle. So the sine of a degrees over its opposite side length is equal to the sine of another angle over its opposite side length, which is equal to the sine of another angle over its opposite side length. So it's important to think of it as that and not necessarily matching up a certain set of ABCs to your problem in question. Okay, for the first thing here, we want to make sure our calculator is in degree mode. So if you have a TI-84, if you can see it here, or 3 or 4 plus, whatever it is, you want to go usually under mode. And this brings up a menu. Each calculator is a little different, but you want to make sure you're not in radian mode, but in degree mode, because we're dealing with degrees. Radian is another way that you can measure the degree measurement of an angle. You can measure it in terms of pi, and that's something that's later on you'll maybe learn when you get to pre-calculus, and it's used a lot in calculus. So in our example here, we have a mock triangle where we have an angle measure of 37 degrees, its opposite side length to be 7, and another side length to be 10. And what I want to do here is find all values of this triangle. So these two angles that are missing, as well as this side length. This is a case where law of sines is beneficial, because when we start plugging into our formula, we have a degree measure and its opposite side length. That is crucial to have. If you don't have that, law of sines really will not work. You cannot solve using that. So I'm going to set it up here as, say, the sine of 37 degrees over its opposite side length, which is 7. And I'm going to set that equal to, now I have to solve for this angle first because I'm given the opposite side length of 10 of that angle. I could not solve for this angle yet or this side length yet because I do not know either one of them. So with that, I can say, okay, the sine, let's keep it form with this. Well, let's say the sine of c degrees, calling this angle c, over the length of 10, its opposite side length. I find it important to get the variable by itself. So I like to get sine of c by itself degrees and not do anything with my calculator till the last step to help alleviate some rounding errors. So if I multiply both sides by 10, I'm left with 10 times the sine of 37 degrees over 7 is equal to the sine of c. Okay? And this is where we have to implement eventually the inverse sine. So at this point, I will type this into my calculator, 10 sine of 37 degrees over 7, and that comes out to be approximately 0.8597 is equal to the sine of c degrees. Now I usually leave this in my calculator, that answer, that decimal goes on forever, because I don't like to round within a problem, but of course, if you like to round within the problem, that's fine. It's just going to be more inaccurate as your final answer. Now we have to do the inverse sine. So if we take, once we have sine of c degrees is equal to some number, we can do the inverse sine of that number is going to equal the measurement of angle c. Okay? So the measurement of angle c, which I've already done in the calculator, and that comes out to be 59.287. And at this point, we have an approximate answer. Okay, I guess this would be approximate too. But these are approximate answers, and they're pretty close to what it eventually, what the exact answer would be. But since we're doing inverse, it is an approximate. Okay, and so this measurement of this angle here now has become 59.287 degrees. All right. Well, now that we have two angles, their measurements, we can find the third angle measurement, because every single triangle, the sum of their interior angles adds up to be 180 degrees. And so if we add 37, or took 180 minus 37 minus 59.287, we will come out with something that's approximate here. Now, it's approximate because we're already rounding this answer, so this answer here has to be approximate. And that's 83.713 degrees. So this angle here we can call 83.713 degrees. Okay, and that's again an approximation. So these two answers now are approximate. And so now we need to find this last side length. Okay, again, we can still use the law of sines to find our answer. Let's get a blue pen. All right. And what I like to do here again is restart with the original angle that we knew and the opposite side, because those are exact answers, so that would give us a more exact estimation. It keeps more of a consistency, so I always like to use numbers that we know to be 100% true that are not rounded as often as possible. So again, I'm going to set up my problem here, if we can see it, that the sine of 37 degrees over 7 is equal to, now I have 10, the opposite side length, sorry, not 10, oof. The sine of 83.713, that's the degree measure we found, over, we want to find the opposite side length. So we can call that just little b. Okay, from now we want to get little b by itself. And so you can cross multiply and then divide by the sine of 37, and you're left with b equaling, now again, this of course has to be approximations, because we don't, this is a rounded answer. That's just technically most teachers will not care on that aspect. And so we have 7 times the sine of 83.713 degrees over the sine of 37 degrees. This comes out to be approximately, with rounding, 11.562, and that's going to be the length here. 562, if you can read that, of that side length of the triangle. Now again, I type this all in my calculator. I wait till the last step, or as late as possible, to type everything in my calculator, so then it gets less rounding errors, so I can see it all at once, and I can follow my math work until the last set of b to make sure that's correct. It's up to you. Some people like to put decimals within, but then you get a lot of variation in your answer. And again, what I like to do is, again, check my answer to see if it makes sense within the problem. And so we know within every single triangle that the smallest degree measure should be the opposite of the smallest side length. And so 37 degrees is our smallest angle. Its side length, the opposite side length, is 7, which is the smallest of the 3. The largest angle measure is 83.713, and opposite of that is 11.562, which is the largest side length, and of course the two middle ones are across from each other. And so that's kind of a way you can kind of quickly tell, said, yeah, hey, I'm probably on the right track, so probably my answer is right. These are hard to double check your work, to plug back into a problem. Of course, you could plug them all back into the sine of 37 over 7, and whatever that decimal should be, equal to the sine of 83.713 over 11.562, and the sine of 59.287, the sine of that is over 10 is equal to the same. So again, you can check that. They're pretty close. There'll be a few, maybe a few decimal points off, but not too much there. So those are two ways that you could check this problem. I hope you learned a lot of sines, and thank you for watching.